So having a continuation on our transformers, it is also important that you do understand this part of your three-phase transformers in your revisions, as we are to consider three-phase. We do understand that's where we're going to be talking of the delta connection, the star connection, whatever that you have. So in a case that there is a star, we can have a star connection, right? Which we can just write as like this. Remember the condition of a star. Then if you consider a delta connection, that's a delta connection. We can just present it this way in a delta, where remember a delta, it gives us a sort of a triangle in the presentation, and this is of a star. There are possible combinations that can actually do happen because you are considering the primary and secondary. This is three-phase. So on the primary side, we are going to be limited. We are going to be having its own. The secondary is going to be on its own. So meaning to say, it's not like to say a connection when it is delta, it's supposed to be delta throughout. No. It can be a combination of n. So we can have possible combinations like the primary can be a star. Okay? And the secondary also being a star. It can happen. Both. Thus we are referring what? A star to a star connection. There can be a condition where it's delta and delta both. This one, it's in delta connection. The secondary is also in delta at the same time. As we're considering delta to delta connection. It can happen that this can be in delta and the secondary can be in a star. So you can have a star, we can have a delta star in that case, delta star connection. We can have it even from this side that we had here, star to delta this time. The primary can be connected in star, then we say the secondary side in what? In delta. So we can have that consideration. So what you need is what are the connections, like how it is presented, as you know, guys, your connections, if it is a star to star connection transformer, that's how your presentation is going to be. If you're considering a star and a delta, primary side in star, secondary in delta, do not worry about that. Okay, considering delta to delta connection, it can be a delta to star connection. That is what you need there, like just to understand your typical connections as they are presented. So with these connections that we are seeing here, all right, I just hope it is not the one that I wanted to read. Okay, no problem. This is the one that I want here. So with these connections that we have, it follows that we need now to understand that all given voltages are line voltages unless otherwise stated. When you're dealing with the three-phase, voltages will be in for the three-phase. Okay, so this one, it's a note that you're supposed to take note here, that all given voltages are line voltages. Or they can be terms of current, unless stated otherwise. Can be in terms of current, line current, unless they state otherwise. Unless stated otherwise, meaning to say, they can give us a condition that it is phase. So as we consider three-phase, remember that's where we talk of the line voltage, and also the one that we consider, that is the phase. We talk of line and phase from our previous level. We had that as long as three-phase. There is line and there's also phase voltages. So in a connection that is of a star, what is it that we understand in what? In a star connection. Whether the primary is the one that we are talking about, whether it is the secondary, or we're just talking about a star connection. What is it that we understand in a star? Remember, in a star, that's when the currents are the same. IL is equal to IP. The phase current will be equal to the line current, meaning to say IL is equal to IP. Either way that you understand, in that case, IL is equal to IP. In terms of the voltages, VL as of a star, remember it is equal to what? Square root of 3 VP, which is the phase. Meaning to say we can have the phase from there. So therefore, from this, if you divide by square root of 3, it means VP is going to be what? VL over the square root of 3 if you divide by square root of 3. That's a star connection. You need to remember this. You're not supposed to forget this as long as you're doing electrical engineering. Delta connection. Remember that? Delta connection. What is it that we had before in our delta? In our delta connection, it is the voltage that are the same. So in terms of the currents, what is the relationship? It follows that IL is equal to what? The square root of 3 IP. So therefore, we can have IP from there if we divide by the square root of 3. So it's going to be IL over square root of 3. Line over the square root of that. So we have got the phase. Talking of the voltages, the line voltage and the phase voltage are the same. This is a delta connection that you need to know. So as we are to relate these, what is important now, because we talk of line voltage, we talk of phase. So as long we have to consider this, guys, in our calculations, you are supposed to use only phase values. Like I said before, here, that values are given as what? They are given as line voltages or whatever that you give, but on calculations, you do calculations using phase values. Do calculations using phase values. What are we talking about there when you're talking about calculations to be made on a transformer? The transformer ratio does not change. The VP that we had, the V1 over V2, but now considered as VP because it's phase. So it's going to be VP1 over VP2. Remember, we used to use this V1 over V2 is equal to N1 over N2 is equal to I2 over I1. So the current and voltage are the one that can be in phase. They're supposed to be phase like this. So the number of tens, guys, is not affected, this one. We move on to the current. So this is the phase current 2 over the phase current 1, just like what we had I2 over I1, but they are supposed to be phase values in calculations. When calculating, you're supposed to make your calculations in what? In phase. So this is, guys, that is the only thing that you need. Nothing has changed from electrotechnology, N3. Nothing has changed on this part, on this introduction. Only part that we're going to talk about in our next class will be parallel operation of transformers. That's where we have got something that we can consider to say now we are talking of our changes that can happen. But in this case, nothing has changed as we used to before. Electrotechnology before. So this is a typical question that we can be given. This is an example that we're having there. A 45 kVA, 6.6 kilovolt as to 400, meaning to say we are given what? A rating of the transformer kVA, kilovolt amperes. So we're given as our apparent power, which is 45 kVA, kilovolt amperes. Then the voltage is V1 over V2, 6.6 kilovolts. V2, which is the 400. So this is V1 over V2, which is 400 volts. So it's just like that. The three phase, we are now talking of what? 3-phase. This is 3-phase that we're talking about. Delta star. Take note. Delta star. So this is just a recap of what we had before, guys. Meaning to say the primer is in delta and the secondary is in star. This is our secondary side. Is used to supply a certain load. Determine the following for full load conditions. A, the primary and secondary phase voltages. Phase voltages. Primary, secondary. What is it that we are given in the first place? We are given V1 and V2. Is there a need for us to use the transformer ratio there? No, there's no need, guys, because this is just a matter of converting to say, because V1, like I said, originally when values are being given, all values are given, all given voltages are line voltage unless stated otherwise. So meaning to say these voltages that we are seeing here, that we are given there, the voltages that we are already given, they are line voltages. The voltage that we are given on this question here, these voltages V1 and V, they are line voltages. These are the ones that we are given. They are line voltages. So we just need to convert them to the primary. I mean to the phase of the primary, secondary, but as phase voltages. So A, remember the primary side. What is it that you are considering from the primary side? It's a delta. In a delta connection, what is it that we understand in terms of the voltages? They're the same. Line voltage is equal to the phase voltage. So meaning to say, the phase voltage that we need in the primary side is simply equivalent to the line voltage that we are given there on that same primary side. So that means that was our condition. We're just going to take as it is. 6,6 kilovolts. We are already given this. This is consideration of what? A delta connection, a delta. VL is equal to VP. Line voltage is equivalent to the what? Is equivalent to the phase voltage. So you're talking of the primary. So you just take that, use as it is. So that was a direct question there. Okay. So considering the secondary, because we also need that of the secondary side. So of the secondary side, how are we going to have it? What is it that we have? It's a star connection that we are given. And what is the relationship of a star? We saw that from a star. We're going to consider this. V phase is equal to V line over square root of 3. The phase there. So meaning to say our phase voltage was going to be V line of the secondary over what? Square root of 3. So that's we're going to obtain this because it's a star. That's a star connection. So remember, I given V2 already. That's the line. Remember, these are line voltages. So that's 400 over the square root of 3. So that was going to give us 230.94 volts, like just like that. So like I said, this is just like our previous part of our electrotechnology. That was the condition there. The phase voltages are there. Okay, so I'm just going to have this one. Then we move on to another part. Because definitely somehow you're going to need these values, guys. You're going to need this 6.6 kilovolts, then P2, the phase voltage of the secondary side, 230.94 volts. All right, let's just leave it like that. Because for the calculations, remember we said we do all calculations in what? In phase. B, the transformer ratio. That is what we have there. And like I said, all calculations now are supposed to be in what? In phase value, using phase values. The transformer ratio can be obtained from any of this. From any of this. What is that we have? Are we having the voltages? Are we having the number of turns? We have the voltages. The voltages are there. So remember that N1 over N2 is equal to VP1 over VP2. Phase values are used. So that is the condition. So you're going to have our transformer ratio there, or our turns ratio, or our turns ratio in short. So you're going to just use the VP there. VP1, we have it 6,6 kilovolts over what? VP of the secondary, which is 230,94. So that's it, guys. Just like that. You're going to have your transformer ratio, which is 28,571. So you can just write it as to 1. Remember the way that you just used before, or you can write it as a fraction. If it is 3 over 1, so means you can just have this over 1. It's up to you. You can just leave it as a whole number like that, but just write it as to 1 like that, a ratio. The secondary line current. From the ratio that we have, they're saying we need to calculate the line. All right, this is C. We need the secondary line current. The secondary line current. It's the line, but in calculations, these calculations are made in what? In phase. They're made in phase, or whatever that you're going to have, they will be in phase in terms. So if there was a ratio that can be used from this, we're going to use these values in phase, but we have a ratio that is complete. There's the turns ratio, which is true, but we check here, we do not have another current because it's supposed to be a complete ratio. If this ratio is supposed to be used, it must be a complete ratio. But we do not have that. What is it that we are given? They gave us the rating. Now it's a 3-phase. This rating, it's a 3-phase that you're considering. So let me also have this on your formulas that in 3-phase, the rating of the transformer is now given as, this is the rating. S is equal to the square root of 3 VL, which is supposed to be the line voltage multiplied to the line current. Supposed to use line voltage in line current. Is it of the primary? Is it of the, say it can be primary? It can be of what? It can be of the secondary. That's the rating now. Our kVA that we used it of single phase. Now you have to use what? The square root of 3. So it's supposed to make that adjustments. So we can see that somehow we can have that because S is equal to the square root of 3, the line voltage times the line current. We need that of the secondary side. So you're going to consider what? The secondary side. So it simply means we can make this the subject by dividing by the square root of 2 and V. So it means our secondary line current was going to be what? S over, going to divide by the square root of 3 VL2 like that of the secondary side, where S is the reactive. I mean that rating that we are given, apparent power that we are given. We have that. So S is what? We have it, 45 kilovolt amperes. So you're going to substitute, everything is there. So that was the 45 times 10 to the exponent of 3 over the square root of 3 times what? The voltage of the secondary, so which is the line of the secondary. Like I said, these are line voltage, the ones that you're given there. So the V2 there is the line voltage there. That's our line voltage of the secondary. We have that. And that is 400 volts. So this is times 400. So with this, we are going to obtain the current of the secondary side. So on the secondary side, the line current was going to be given as 64.952 amps. If we are to use our calculators properly, that is what you are going to have at the end. So you just have to be careful because not always where you are given this complete information. If there was somewhere where the phase is there, then you're going to consider that. Okay, so let's just take this value. We're going to need this 64.952 amps. This is the line current, considering line current. But now, look, they're saying the primary phase current, What are they trying to do? What are they trying to do here? Okay, let's take a read of something here in our calculations. They want you to calculate the primary phase. But do we have anything from the primary side? Do we have anything from the primary side? If you were to consider that from the rating, there are two ways that you can actually, from the rating, remember the rating is given as S is equal to, because this is three phase, VL, IL like this. If it is the primary side, I'm going to consider as 1, 1. I'm calculating line current of the primary. But if you consider that I'm calculating the line current and you check there on another question, what are they saying on E? Calculate what? The primary line current on E. So meaning to say there, they wanted you to avoid this, but we could have used it. You calculate the line current first, then you convert it to what? To a phase, because you are working with a delta. So you have to consider what is it that happens in a delta. But is by the look of the question, what is E? It is to calculate this now, E. So meaning to say we are forced now to use any other formula besides this one, because they will need you to use that one. But if you can even use that, there's no problem. Then you just write the answer on E. I'm not saying it's wrong. So, but let's try to figure out other formulas. We are in a phase, and in a phase, we do understand that in a phase, the relationship does not change. N1 over this from the tens ratio that we got, because we've got our tens ratio. So it follows 28,571 over 1, which is our tens ratio, must be equal to VP1 over VP2. In terms of the currents, it must be what? IP2, the secondary over what? Secondary over primary. Considering what? The phase, like I said. These are supposed to be phase values. And we need to calculate this, but we do not have this. Because from the secondary side, we did not calculate the phase. No, we calculated the line. So the question was to bring us to the line. I mean, from the line to the phase, from this to the phase that corresponds to that. What is the phase current of the secondary side? So in the secondary side, what is that we have? It's a star connection. That's a star. Remember our secondary side. Our secondary, we are dealing with a star. And what is it that we understand in terms of the currents? If we are in a star connection, the phase current and the line currents, the same. So meaning to say, therefore, IP2 there was going to be equal to the same as 64,952 amps, because we are dealing with a star. In a star, the line and the phase currents are the same. So nothing has changed. We're just going to use that value here. So meaning to say we have this value. Now we can calculate this IP of the what? Of the primary, the phase. So it's going to be 28,571. Guys, here you can even use this one. Remember, we got it from where? This, we can even use as it is, like this one here as it is. This fraction here before. I'm not saying that one you can, because that is where we took it here. We can take it as it is here and equate to this, or you can take it from here, because that is the same thing that you calculated. So it is equal to what? The phase current of the secondary side. What is the phase current? 64,952. It was just that they are the same. There is no change from what we had before over what? The primary side, the phase current. So we can calculate this phase. So what was going to be our answer? So just try to cross multiply That was going to be 28,571. IP1 is equal to 1 times this, which is 64,952. You need to calculate the first, so definitely divide by what? 28,571 divide by 28,571. So that was going to give you the phase current of the primary side, which is 2,308 amperes. So with this, we have got our answer. So they wanted you to avoid that other formula, but we could have used it. But from that, we are going to calculate the line current, the one for S, our rating of the transformer, because S can be given as the square root of 3 VL. But they had to calculate now the line. But look now, they're asking to calculate for that line current here, the primary line current on E. So what is that you have to consider? Because you have got the phase. So this one is just a conversion now because you have the phase already. So to find the primary line, it's line from phase to line, you have to consider the connection there. Primary is what? It's a delta. So let's consider in a delta connection, what is it about the relationship? IP is equal to this, or it is line. Line current is equal to square root of 3 of what? IP. In a delta connection, because the primary is limited to a delta connection. So that was the idea now of this question, all right? So with this, you were going to calculate it that way. That is on E. So from a delta connection, it is going to follow that that is our line current, considering the primary is going to be the square root of 3 of the phase current of the primary. So that's square root of 3 times the phase current of the primary. We calculated this. We got, that was 2,308. 2,308 amperes. So that was going to give us that of the primary side, which is the line, which is 3,998. So it was going to be 3,998 amperes. So we have got what? The primary line current. So let's think about this one to say if another way that we could have obtained it. Remember, from the three phase, another way S is equal to the square root of 3, say that will be VL IL. Considering the primary side, these are line values. So we need this line current. So the line current one was simply going to be S over what? Square root of 3. That was going to be VL1, like that, of the line. So that's the line current of the primary side. S is given 45. That is 45 times 10 to the exponent of 3 over the square root of 3 times the line voltage. And this line voltage, remember, or like I say, that the calculations or the given values, they are already for the phase. I mean, they're already for the line. This one that you're already given, they're already for the line. So the V1 is already there. This one, the V1 is already there, the 6,6. That's 6,6 times 10 to the exponent of 3 as the line voltage from the information that we are given. So you can even cancel the 10 to the exponent of 3, as we can see that this is the same. The 10 to the exponent is going to cancel. So it was going to be 3,936 amperes, something like that, if you are using this one. 3,9. If you check this one, it was 3,9 because of the rounded off of values. We rounded off. Remember, there's a rounded off figure that we are using. And that rounded off figure, which is 2.308, this one, it was also obtained from rounded off values. So it is not going to give us that exact, but use your values that you're obtaining, guys. They are going to mark according to what you are using, right? So it can be that way. So we just need to revise as much questions as we can in our revisions, understand this typical part of the connections that are being made between the primary side and also the secondary side. Is it that it is a star? Is it that it's a delta? And also understanding the rating of our transformer, which is given in our volt amperes, which can be taken from the primary, which can be taken from the secondary side. And with this, We're going to answer as many questions as you can for these basics. So we shall see in our next class, working, like I said, with the continuation of the parallel operation of our transformers. So we shall see, guys, with our time. Thanking you guys for joining our membership, which allows us to have these videos. And to members, we give you the Thanksgiving, guys, to say thank you for joining the membership. Let us also continue to have others to the channel so that this can help us also to grow our classes in our daily activities as we are revising for the exams that are ahead of time. Let us try also to add as many question papers in our revision that can actually help to understand now these basics that we just had now.